Hello there. I'd like to welcome you to the Chapter 17 review, also called the Chapter 17 Study Guide. And it should be noted that letter E is not mine. It's not my fault. So we got 20 questions today, and here we go with question number 1. So I'm drawing a nice box for you. So let's talk about first the 3 forms of stress. Okay, so here we go. So what type of stress am I showing now as I push on the block? Okay, this is compressional stress. Okay, here comes the second form of stress. It's the same box, but it's a different type of stress. What type of stress pulls the box apart? Okay, this is tensional stress. And then the third one, I'm kind of getting fancy by drawing a squash box or a parallelogram. And what type of stress am I showing now? Okay, this is shear stress. So based on these 3 forms of stress, compressional, tensional, and shear, so from these 3 choices, which one, letter A, shortens the crust? Which one shortens the crust? Okay, this is compressional. Which one actually stretches the crust out? Okay, this is tensional. And of the 3 forms, which one is found along a strike-slip fault? Which one is found along a strike-slip fault? Okay, that is obviously shear stress. So question number 2, now we've talked about the 3 types of stress. We're now going to consider the 3 forms of strain. So letter A, this is a form of strain that will bounce back to its original shape after the stress has been released. And we'll get to the answer here in a minute. This one does not bounce back to its original shape. It does not return to its original. And the third form of strain is what happens if something will break. So the first one, bouncing back to its original shape, is called elastic. If it does not, it's known as plastic. And then if something breaks, it is brittle. Okay, so we're going to use this knowledge in this picture. So this is a real-world picture, not taken by yours truly. What type of likely stress was involved in creating this structure? Probably compressional stress. And how have the rocks behaved in response to that stress? Well, they have strained plastically. They will never bounce back to their original shape. So now your job in question number 3 is to fill in the blank. This is the rule of thumb for deformation. And the rule of thumb is that rocks would rather do this than to do this. So what goes in the first blank? Okay, this is bend, and then they'd rather bend than break. So let's do a follow-up with this. If you have rocks that are bending, it's creating geologic structures which start with the letter F. These are folds. And then if rocks break, they can either have displacement or not. So if they do not have displacement, they're just cracks in rock, which starts with a J. And if they do have displacement, they start with an F. So those are joints or faults. So question number 4, I have a nice cartoon type diagram for your consideration. Okay, are there folds located in this diagram? And the answer is yes, because I'm highlighting them in yellow. Do you see any faults in the diagram? Okay, if you look very carefully, there are 2 faults right here. They're not quite touching one another, which indicates that there's been slight displacement between the 2 of them. And then there's 2 more up here with T and P. Question number 5, I'm going to draw 2 things which are different, and I'm labeling them A and B. Okay, between A and B, the top or bottom diagram, which diagram is actually showing you cross-bedding? Which one is cross-beds? Okay, that's letter B. Which one are simply showing dipping beds? This is letter A, because letter A are planar beds that have been tilted over. Question number 6. Let's go over the attitude of bed choices. The attitude of bed choices with diagrams. So these layers are in this attitude starting with an H. They are horizontal. These beds are doing what? They're dipping These beds start with a V, they're vertical, and potentially they can be completely flipped over starting with an O. These are overturned. So this is question 6A, and this is a picture that I grabbed off the internet. What is the attitude of these beds, would you say? Okay, the answer that I've written here in docere is nearly vertical, because I don't think the rocks are completely 90 degrees up and down. I think they're maybe 85 degrees or something like that. Or they could be overturned. You need more evidence of that. Question number 7, let's go over the two components of dip. Do you remember the two components of dip? And it's not onions and sour cream. It starts with a D and an M. This is direction and magnitude. So using this knowledge, we're going to apply this now to some strike and dip. So here I've drawn a strike and dip symbol for your consideration with a number on it. So what is the dip of this rock or whatever? And remember, dip has two components, direction and magnitude. So the magnitude is 70 degrees, but it's dipping toward the north because the little tick is inclined toward the north. Okay, what is the strike of these beds? Okay, strike is always a two-directional component, so these beds are striking east-west because it's always perpendicular to dip. Okay, here's another one for your consideration. So let's go over the dip first. What is the dip of this layer? Okay, it's 12 degrees to the southwest. And what is the strike? Well, in this one, the strike would be northwest, southeast. Okay, so enough of that. We're going to get into this picture now with question number 8. So what in the world is this? What is it showing you? And this starts with the letter F. It's just a simple little answer. Okay, this is a fold. So here's another continuation of this same picture. So what I've done is that I've accentuated parts of this fold for you in yellow, and I'm also drawing another part here in red. Okay, so this red part, what does that indicate? Okay, this is connecting all the points of maximum curvature in this fold, and that is called an HP, or the hinge plane. Okay, so we're going to return again to this picture and consider more about this hinge plane. Okay, this hinge plane is dipping, so for sake of argument, let's just say that it's dipping. Would this be a syncline? The answer is yes, and I've given a check on that. It isn't a syncline. So since the syncline has a dipping hinge plane, would you call this fold plunging or overturned? This is an overturned syncline. So question number 9, 3 folds. I kind of jumped ahead with that previous picture, so now we're kind of getting back to the basics. So the first fold on the left starts with an A, the second one starts with an S, and the third one starts with an M. So in order they are anticline, syncline, and monocline. So let's consider this anticline. Right here is a point of maximum curvature called the hinge point. So coming out of the docere presentation is a line that's connecting all the points in that single bed. So that line is representing what line? Okay, this is a hinge line. So now I'm drawing 2 completely separate folds, and I'm labeling them A and B. So between choices A and B, which one is representing an overturned fold? Okay, this is letter A because the hinge plane is dipping. Letter B, he's called recumbent, which is typically a fold type that I don't talk about in class. So this is question 11B. What folds are in the picture? How many folds and what type of folds are shown in the picture? Well, let me help you accentuate them with my black marker here. That one starts with an A. That's an anticline. And here we have the S one, which is a syncline. And by the way, do they look plunging? Okay, well, it's kind of hard to tell in the picture. That would mean that their hinge line is dipping, not their hinge plane. So now what I've got in question number 12, I've got some really old rock, maybe Precambrian in age down below, and all the beds are dipping away from this really old rock. So would you consider that a dome or a basin? Okay, that would be a dome. Okay, the follow-up to that is the complement of a dome. So if it's not a dome, it must be and this is a basin. Okay, question number 13. What you're looking at here is Texas, but it's a very special map of Texas, which is called a geologic map of Texas. This shows you where all the rocks are on the Texas's surface. So right here in the center of our state is very old rock, which is known as the Central Texas Uplift. This is what this physiographic province is called. And these rocks are Precambrian in age. So is that structure likely to be a dome or a basin if it's Precambrian? And the answer is it's a dome because all the rocks around it are dipping away from that structure. Okay, so here's the next part of question number 13. What I've done is that I've blown up the picture a bit and showing you what the rocks are doing, or the layers are doing, between Austin, San Antonio, and Houston, Corpus Christi. So these rocks, these layers, these beds, which direction are they dipping? Okay, and the answer is they're all dipping to the southeast. Okay, so basically the rocks are getting younger and younger and younger as you travel toward Houston from Austin. So this is a very old picture from a very previous chapter, and as you recall, this is a dike. It's a discordant tabular pluton, but I'm more interested in this crack. So what is this crack called? Well, I don't see any evidence of displacement, so you would call that a joint. And what has caused that crack or joint to form? And the answer is that it's been formed by some type of regional stress, compressional, tensional, or shear. So question number 15, we're nearing the end. I got 5 more questions to go. In this diagram, there's something labeled E. And is E a joint or a fault? And E is a fault because there is evidence of displacement. Now I've labeled the 2 blocks with A or B. So which block is a hanging wall? Okay, that's letter A. And which one is a footwall? That is letter B. Okay, so E is not just a line drawn on a piece of paper. If this were a real-life situation, it would actually be known as the FP, or the fault plane. Okay, so same diagram, different picture. E, is it showing you a dip-slip fault or a strike-slip fault? Okay, this is dip-slip. So to continue that thought, is this a normal dip-slip or a reverse dip-slip? Okay, it's normal, and these are relative motion arrows to help you decide that. Same picture, different question, 15C. So what type of regional stress arrows would you draw on this diagram to show how the displacement has gone? How would regional stress arrows be drawn on this picture? Is this correct? The answer is yes, because if I do that, then this hanging wall block will move down. Question number 16. This is a real thing in the real world, not taken by me. So your job is to count the number of faults in the picture. Good luck. Okay, what I've done is that I've tried to draw on all the faults that at least I can see, and I actually count 7 of them, but I'm sure there's a lot more in this picture. There's some that are easier to see than others. Okay, so let's go a little bit more in depth in this picture, and let's look at only one of these faults at a time. So let's consider this fault right here. Would this be a normal or reverse fault? Okay, he is normal. And let's look at this one over here. And what I've done is I've accentuated the displaced beds for you. Same question, normal or reverse? Okay, this one's a little tricky because if I apply relative motion arrows and considering the orientation of the fault plane, I have to say that this is a reverse fault. Question number 17. You're going to see this diagram in many preceding slides, so one thing at a time. What is the attitude of beds in this first little picture? Okay, they're horizontal. Okay, what type of stress is shown here in this next one? Tensional. And now, compressional. What type of stress in this one? Compressional. And now, shear, here, compressional, and this one, the same, compressional. Okay, now what your job is to do is to mark which ones are dip-slip faults. So where are the dip-slip faults? Are these the only dip-slip faults shown in this picture? Yep. 17C, now you're to name the fault types only. Name only the faults. Okay, so what's the name of this one? And here, and here, and here. So I'm adding some letters now. So this one starts with an N. This one starts with an R. This one's a special type of R that begins with a T, and this is the SS. So in order they are normal, reverse, thrust, and strike slip. 17D, now we're going to consider the bottom two pictures finally. Which one is a syncline, A or B? Okay, that's letter B, and obviously which one is an anticline? And that is letter A. Okay, finally we move on to question 18. We got 3 more questions. What type of fault is shown in the picture, please? Okay, this is a strike-slip fault, but it's actually a transform boundary between 2 tectonic plates. Okay, so what is the O word in number 19? The O word used to describe a mountain building episode or a mountain building event, such as when Africa slammed into North America and made the Appalachian Mountains. So this O word you're looking for is orogeny, that describes any mountain building process, such as shown in this picture. This is also an orogeny. So let's say out here in the geologic past, I had some volcanoes in the water, and for whatever reason, geologically speaking, they got sucked up underneath this continent, and they're now, the remnants of them are found underneath the continent. So this is a concept that I may have talked about in class, of an adding on to a pre-existing continent by other crustal material. So do you remember what that was called? Okay, this is a special type of tectonics called accretionary tectonics. And with that, this concludes our Chapter 17 study guide.